Alright guys, last week we talked about uniform circular motion, and several of you weren't here and have asked me to make a screencast, so I'm going ahead and doing that for you. So when we talk about uniform circular motion, we're talking about an object that moves in a circular path and with a constant speed. But while the speed is constant, the velocity is not constant, because the object, to remain in a circular path, is constantly turning, and so the direction that it's moving is constantly changing, which means the object is accelerating. So when you have an object in circular motion, the velocity is always tangent to the circular path. So let's say we had an object traveling around this circle we see here, and it's going in a clockwise direction. So if our object was up at the top of the circle, then its velocity would be to the right if it was traveling in a clockwise direction. Of course, if it was going counterclockwise, it would be to the left. By the time it made it down to the right side of the circle, now the velocity would be straight down. By the time it made it to the bottom of the circle, the velocity would be to the left. By the time it made it to the left side of the circle, the velocity would be up. And if it was somewhere else other than top, right, left, or bottom, let's say for example it's at about the 1:30 position, if we were looking at this as a clock, then the velocity would be down and to the right at a 45-degree angle right there. Alright, now if we wanted to find the speed of the object, then of course speed is always distance divided by time. But there's also a special equation we can use for uniform circular motion, where we use the time it takes to get around the circle one time. Okay? And of course, if we travel around a circle one time, then the distance we've traveled is the circumference, and we can always calculate circumference using 2 pi r, where r is the radius of the circular path. And then we would divide that by the time for one circle. Okay? And uniform circular motion is a cyclical or periodic motion. It repeats itself at regular intervals. And so when we talk about the time for one cycle, in this case that would be the time to get around the circular path once, that's usually called the period, and a symbol that's commonly used for period is a big T. So it's still a time, but more specifically it's the time required for one trip around the circle. Alright, so as we said earlier, if the velocity is constantly changing direction, then our object is accelerating. Anytime we turn, we are changing the direction. And the direction of the acceleration is, if we're in uniform circular motion, is always exactly towards the center of the circle. And the proof to show that, actually to really prove it, requires calculus. Okay? And we went over a little bit of a proof by showing vectors of final and initial velocity in class. We're not going to go over that here, so you're just going to have to trust me that for right now, in this situation, let's say you were in a car moving in this circle, looking at it from above. Basically, you're constantly turning your car to the right if you're going in a clockwise circle as viewed from above, and so you're constantly accelerating your car to the right. Now, we can also calculate that value for that acceleration, and the only way to prove this at all does require calculus. So you're just going to have to trust me again that the centripetal acceleration, we'll talk about what the word centripetal means in just a second, is always going to be equal to the speed squared divided by the radius of the circular path. So what you can see there is if you're traveling the circle at a higher speed, then your centripetal acceleration would be greater. Or also if your circular path is smaller, if it has a small radius, then that's going to require a higher centripetal acceleration. Now we call it centripetal acceleration because it's always towards the center of a circle, and that's what the word centripetal means. So the word centripetal means towards the center of a circle. Now, Newton's second law tells us that if we are accelerating, then there must be a net external force acting on our object. And in this case, if we're accelerating towards the center of the circular path, then the net force must always be towards the center of the circular path, and so we call that force a centripetal force. Now, that centripetal force could be gravity, it could be friction, it could be tension. There are lots of things, it could be normal force, there are lots of things that could be supplying the centripetal force. So centripetal force just means a net force towards the center of a circle. And of course, Newton's second law tells us that net force always equals ma. And so it's a very simple substitution to say that net force is equal to mv squared divided by r if we have an object in uniform circular motion. Alright, the other thing we talked about last Thursday was when we have friction as centripetal force. Examples of that would be like a coin sitting on a record player that's turned on. Another example of that would be a car driving around in a circular path as long as the curve is not banked, as long as the road is completely flat, completely horizontal. And in both of those situations, it's actually static friction causing the object to turn and to complete that circular path. So if we were looking at an object from, let's say, the front or the back that's traveling around in a circle, so that box is a car, and let's say it's heading straight towards us at the moment, but it's turning to the left. So what that would mean is that the static friction is pointing to the car's left. The car is coming towards us, so that would be our right. Okay? So basically we're saying that this is the center of the circular path. Alright, and so when we have that situation going on, the other forces acting on the car would be the weight going down and the normal force from the road pushing up. And as long as we're ignoring air resistance and our road is completely flat, those would be the only three forces that are acting on our car or the coin on the record player, whatever. Okay? In the vertical direction, the car would be in equilibrium, so N has to equal mg because the net force in the y direction equals 0. But the net force in the x direction is going to equal ma. And so what we end up with is our force of static friction equals mac, or mv squared divided by r. Now, most of the time when we're doing a problem like this, the question is going to ask, what is the minimum coefficient of static friction required to make the turn without sliding off? Or what is the maximum speed at which you can make the turn if this is the coefficient of static friction? And so basically what they're telling us for that problem is that the Fs is the Fs max. And if Fs is the Fs max, then mv squared over r would have to equal mu s times n, Alright, but we already said earlier that n equals mg, so we can say then that mv squared over r equals mu s mg. And then our m's actually cancel out. And so we're left with this v squared over r equals mu s times g. So, in that situation, if you want to solve for the maximum speed at which you could make a turn, then you'd solve that equation for v. And v would equal square root of mu s gr. Or, if we want to know the minimum coefficient of static friction required to make a turn at some speed, then that mu s would equal v squared divided by gr. Okay? So this setup of this free body diagram and setting Fs equal to Fs max is a very common concept that you need to understand to address questions like what is the maximum speed at which you can make a turn, or what coefficient of static friction is required to make a turn, etc. Alright, so that was the main content you guys missed last Thursday, and I hope this screencast helps you out. Bye.